Okay, so thanks to all the organizers for putting together this great program. So I actually was a student in a version of this school that occurred in the previous millennium. And so actually I met a lot of people who are going to be lecturing or have lectured already in the school. So I think it'll be a great experience for you guys as well. I actually don't remember any of the lectures, but it was still very nice. Okay, so let's see. So I finally came up with a title for these lectures. Okay, so I'll mainly be talking about interaction effects. So you've heard a lot about topological insulators and essentially thinking about these phases in terms of free fermions. Okay. Okay, and the new thing that we'll try to add is interactions, and we'll really be interested in new conceptually new physics that arises once you add interactions to these topological insulators. Okay, so let me start by giving you a preview of the kind of results I'd like to get to. And the first will be about new phases. So one of the things we'll talk about is how interactions can give you new phases of matter that you might think of as being analogous to these topological insulators. Okay, so part of the way in which we'll make progress is really to define what we mean by a phase that's like a topological insulator. Okay, so we'll be talking about new interacting phases that are like or integer quantum Hall states. Okay, so what does it mean for a phase to be like these phases, but nevertheless include interactions at some fundamental level? Okay, so once we actually make that definition precise, which is what I'm going to spend the first half of the lecture today, we'll see that we can actually expand the list of topological phases, and one of the big surprises has been that phases of matter that you thought of as being fairly well understood, for example these integer quantum Hall states, were in fact people were actually missing some rather fundamental physics that should be also thought of as being analogs of the integer quantum Hall state. Okay, so of course for the integer quantum Hall state we know that there's a quantized Hall conductance, and you quantized in units of E squared over H, and there's an integer over here. Okay, so you might think, and this is what people believed, that even with interactions, the set of phases that you could think of as integer quantum Hall states are defined by just this integer. Okay, so the classification would simply be an integer, and you pick an integer, and that gives you one of these phases, and that's all there is to the integer quantum Hall effect. Okay, so what you have realized in the last couple of years is that this is actually incomplete. Okay, there's actually a bigger set of phases that you should rightly be calling integer quantum Hall states, and the true classification is not just integer, but a pair of integers. Okay, and this new set of states only appears in the presence of interactions. Okay, so we'll try to work our way towards this result, and the way we'll do that is to, take what seems to be a bit of a diversion. We'll actually think about topological phases of bosons. Okay, so and for the purpose of this talk, I won't really distinguish a boson very much from a spin. In both cases, you have excitations that have trivial statistics under exchange. You can think of them as spins or bosons. To some extent, it depends on your taste. But we won't actually include fermions to begin with, just to emphasize the fact that we are going to talk about strongly interacting systems. Okay, so when you have phases of bosons or spins, you have to include interactions to get anything non-trivial. So we'll automatically be thinking about interacting phases of matter. Okay, and then we'll come back to the question of what happens when you combine them with fermions, with electrons, for example, and come up with a complete list of these phases. Okay, so that will actually be the plan for today, or at least I'll start talking about these sort of new phases, and later in the lecture course, hopefully I'll be able to get to the second topic, which is new phenomena that arise in the presence of strong interactions. Okay, so a number of things that we learned from the free fermion description of topological insulators. It turns out to be sort of an approximation. The free fermions give you one very useful perspective on topological insulators, but it turns out they're not the entire story. Okay, so one of the new phenomena we'll see. So again, just to give you a preview of what's going to come later, is that we sort of have this idea that you always have, let's say I have a 3D topological insulator. So the surface of this topological insulator we associate with the Dirac cone. Right? So it's a metallic surface. Okay, and if you wanted to make the surface insulating, the general belief is that you have to break time reversal symmetry. Okay, so you add some magnetic impurities and gap out the surface of this three-dimensional topological insulator. Okay, so okay, but what we have realized, again, quite recently, over the last year or so, is that this is not the only way in which you can get an insulator. Okay, on the surface, there's actually a way to get an insulator with strong interactions that does not break time reversal symmetry. Okay, and it's an exotic kind of insulator. We'll talk more about that later. But this will give you an idea of the kind of phenomena we're going to be interested in. Things that are conceptually new, but have to do with phases that are, we think we know pretty well. Okay, so that'll be sort of the two sides of this course. One will be new phases, and the other will be aspects of phases that we know about, but you get new phenomena because you consider the effect of strong interactions. Okay. Okay, so. Okay, so let's first talk about new phases, and to do that, we'd actually like to define, properties that could help us identify a state of matter. Okay, so when you say there's a new state of matter, how do you know that it is really a distinct state? So let's talk a little bit about phases of matter, because we're going to eventually talk about a new phase. And I'll really be interested in quantum phases of matter. So we'll be thinking about states that are at zero temperature. Okay, so we're really looking at the ground state of some particular Hamiltonian. Okay, and so we'd like to know what property could we use to distinguish different phases of matter. Okay, so this is something that many of you have probably heard before, or been exposed to in some form. But let me quickly go over this, because it will help me get into this question of what does it mean for a phase to be like a topological insulator? Okay, so for a long time it was believed that you have different phases of matter because you break symmetry in different ways. Okay, so one way to get different phases of matter is by spontaneous symmetry breaking. Okay, and a simple example is you can take a chain of spins. Let me actually write this out in some detail because I'm going to use it for something else later. Okay, so I have, let's say in one dimension, I have a chain of spins, or two-level systems if you like. So each spin has two states, up or down. Okay, and you can think of this as a low symmetry magnet, where we'll only have a single symmetry, which is spin up to spin down symmetry. Okay, so you can write on some Hamiltonian. Okay, the quantumizing model, there's one term that likes to make the spins parallel on adjacent sides, and there's another term that competes with it, which is a field in the x direction. Okay, so this Hamiltonian has two phases. If this coupling G is very small, or 0, for example, you simply worry about this term. You align all of the spins, and that ends up breaking the symmetry. Okay, so you have all spins up, or all spins down. Okay, that's kind of a caricature of the state as a function of G. Okay, so this breaks symmetry, breaks up to down symmetry. Okay, and then as you increase G, at some point you lose the symmetry breaking. You end up with a unique state where all of the spins are aligned along the field. Okay, so clearly this model has two phases, and what's the distinction? The distinction is that in this particular phase, in the small g phase, there's a symmetry of the Hamiltonian. Sigma z goes to minus sigma z, which is broken by the ground state. Okay, so if you just look at the expectation value of sigma z, naively you would expect that to be 0, but this is non-zero when you're in this symmetry broken phase. Okay, and a characteristic of all of these definitions of the phases of matter is that these definitions only become sharp if you have a very large number of spins. Okay, so so we'll always be looking at ground states, and we'll be looking at the size of the system going to infinity, okay, in order to define something as a phase of matter. Okay, so so when you go from one phase to another, there's a transition. You can think of that as the basic way in which you define a phase of matter. And over here, the transition is guaranteed by the fact that you break symmetry. Okay, so the importance of symmetry over here is pretty clear. For example, if I were to break the symmetry by just putting on a field along the z direction, okay, then there's really no sharp distinction between these two phases. And in fact, this transition would be wiped out typically, and you'd simply have a crossover. You could just go smoothly from the left to the right in the absence of symmetry. Okay, so for a long time, people thought this was the only way in which you can have a distinction between phases. Okay, that if you had two states which have the same symmetry, they're actually the same phase. Okay, but there's a simple example that was cooked up by Wegener. He wrote on a model which has two phases where both the phases have the same symmetry. Okay, and let me mention that model. It has a modern kind of reincarnation, which is the toric chord model. Okay, so I think Claudio talked in detail about this model. So let me just mention it because I want to draw a distinction between states of this kind and the states that we'll really be interested in, the ones that are like topological insulators. Okay, so the toric chord model, you've got spins on the sides of a lattice. Okay, so there are two kinds of plaquettes in this model. Shaded ones and the empty ones. You have some spins, again, these two-level systems. Okay, but the Hamiltonian is a product of these four of these spins around a plaquette. or again 4 of the spins around the empty, around the unshaded plaquettes. Okay, but with the x component of the span. Okay, and you can add terms. Actually, you can add any term you like to this Hamiltonian. As long as it's small and local, it will turn out that this phase is not affected. Okay, so let's add something. Let's say, add some fields along the transverse directions in such a way that this model has pretty low symmetry. Okay, in fact, it doesn't have a Z2 symmetry unlike that model. Okay, so from the point of view of symmetry breaking, you would think this model wouldn't have 2 phases. It should just have a single phase. But in fact, as I'm sure all of you know, if you draw some phase diagram, let's say with these fields as the axes, you find in fact it does have 2 phases. Okay, there's a phase here, which is a topological phase, and it's always separated by a phase transition with the phase which is at large fields. Okay, so if you have a large field, you can just think of it as polarizing the spin. That's a very simple looking state. Okay, ultimately it's a very simple looking state. It's simply a product of spins being along some direction. Okay, but when you go into this part of the phase diagram, there's another phase that appears, which you can analyze by going to the special point over here, where you switch off these fields. And then you realize that this phase has got, you satisfy both of these constraints, and you get a ground state. But this ground state has no, there's no product state representation. You cannot write it simply as a product of individual spins doing something that is producted over the entire lattice. Okay, there's really some quantum entanglement between what the spin at a particular site is doing and what all the other spins are doing. Okay, and it's useful to kind of think about this, the thing that's special about this topological phase as being some kind of long-range entanglement. Okay, so there's actually a way to define the unique features of this phase using the notion of entanglement. Okay, but unfortunately we don't have time to do that today. Maybe you've heard it somewhere else in one of the other lectures. But we'll try to specify what this means for a topological phase in terms of some like physical characteristics. Okay, and one of the characteristics about this phase is that you have excitations Okay, so you have excitations that have some non-local interaction with one another. So there are 2 kinds of excitations you can make. You can pick one of these plaquettes, and the way the Hamiltonian works is that it comes with a minus sign for this plaquette product. So you'd like the product of these spins to be unity, okay, plus 1. Okay, but you can make an excitation by flipping that sign, making that sign minus 1. And that will be some gapped excitation in this topological phase. Okay, and there's another excitation like that where you do the same for this type of plaquette. Okay, there are 2 kinds of point excitations, and it turns out that this pair of excitations has some mutual statistics. Okay, you take one around the other, even if they're very far away, they can see each other through a Berry's phase. Okay, and so this is some sort of anyonic statistics. It's very analogous to fractional statistics that you see in the quantum Hall effect. But in this particular case, the unusual statistics is between pairs of particles. Okay, so that's a feature of a long-range entangled phase. You have excitations that have some unusual statistics. It's not what you put in. You just put in bosons or spins in this model, but you get excitations that have unusual statistics. Okay, that's one way to diagnose that you have a long-range entangled state. Another way to diagnose is if you put the system with periodic boundary conditions. Okay, there's actually some ground state degeneracy. Okay, and again, I think this is something Claudio probably talked about. You can wrap this around on a torus, identify this on that side, this on that side. You have the system on a closed manifold, and you find that there are these 4 states that are nearly degenerate. Okay, and they become more and more degenerate as you go to larger and larger system sizes. Okay, now, degeneracy of the ground state itself is not a characteristic of a topological phase. And after all, if you look at this particular example, there's a degeneracy in this ordered phase, all spins up or all spins down. But in this particular case, there's no way to tell between these different states by making any local measurement. Okay, there's a set of degenerate states, and there's no local distinction. Okay, so that's why this is a topological degeneracy. If you make some local measurement, you'd never be able to tell between these degenerate states. Okay, in fact, that's why they're degenerate. The Hamiltonian itself is a local operator. Okay, and the Hamiltonian is not able to tell between them. They end up having the same energy. Okay, and again, this degeneracy appears in the limit of very large system sizes. Okay, so we'll use these two as characteristics, either one of them as a characteristic of long-range entanglement. Okay, and the main purpose of doing this was, try to see within this way of thinking about the states of matter. So now we have 2 ways to have a distinction between states of matter. You can have breaking of symmetry, or you can have this kind of topological distinction. Okay, where you have one phase which has exotic excitations with mutual statistics, or this ground state degeneracy, and another one which does not, okay, which is more trivial. Okay, so you can ask the question, is that the complete list? Are these the only 2 ways in which we can have distinctions between states of matter? Okay, and the answer is no, of course, because it turns out that topological insulators do not fall in either of these categories. Okay, so if you take a Z2 topological insulator, of course, there's no spontaneous symmetry breaking. We're thinking of something which retains all of the symmetries. But on the other hand, if you take this topological insulator, put it on a torus, you have a unique ground state. You look at excitations in the topological insulator, all the particle-like excitations, which have short-range interactions, they're all just electrons. Okay, there's nothing new that comes out there. Okay, so it doesn't fall into either of these classes, and so in a way it defines a new class, which is the class that we'll be interested in. So we'll be interested in states that are not long-range entangled. Okay, so we'll call them short-range entangled states. Okay, so these will be, we'll work just with gap states. Okay, they're all gapped, and they do not have okay, with periodic boundary conditions, you do not have ground state degeneracy, and you do not have excitations that are different from what you put in. Okay, so just put a negation over here with all of these statements. That's a short-range entangled state. Okay, that's how we'll define a short-range entangled state. Okay, and we'll assume that there's no symmetry breaking. There may or may not be a symmetry, but if there is a symmetry, it's a symmetric state. Okay, so this is a way in which you can try to distill what is the essential physical features that go into defining a topological insulator, or states like topological insulators. Okay, it's having a distinction between states of matter without going so far as to have this type of long-range entanglement, but on the other hand, still being distinct from the symmetry breaking kind of idea. Any questions? Does it make sense so far? Or? Yeah.
Are there any other models with long-range entanglement, like Lattice model? Can you give some examples?
Yeah, so there are many models like this. So, any state that's not gapped, if you have gapless excitations, for example, a Fermi liquid, that would be a state with long-range entanglement of a different kind. Okay, but if you talk about gapped states, then long-range entanglement always implies this type of physics. Okay, and another example, maybe more physically relevant, is you take the Laughlin state at 1/3 filling, and that's a state that also has exotic anion excitations. You put it on a torus, it has threefold degeneracy, and there are analogs of this in 3 dimensions as well. You have states which have these kind of features. With periodic boundary conditions, you have ground state degeneracy. Okay, so there are many models, and there's a lot of work on trying to extend these ideas. And most of the extensions are sort of direct, and the essential ideas are captured by this model. Okay, we'll see later that there's some weird connections between states like this, short-range entangled states, and states with long-range entanglement. Okay, so in particular, if you look at 3-dimensional states with short-range entanglement, there's some connection to 2-dimensional states with long-range entanglement. Okay, so there are all kinds of connections over here that people are still trying to figure out. And in some sense, you have to know the whole picture rather than looking at only pieces of it. Okay, but let's focus on this for the moment. Okay, so just to give you some flavor of how it helps to have a definition like this, it turns out as soon as you make a definition of such states, even before you write down any model, you can actually derive some logical conclusions. Things that follow just from the idea that you have states which have short-range entanglement, but nevertheless there's some distinction between them. Okay, so all of these states, the way in which you get some physical richness over here, just like with topological insulators, is that although all of them have the sort of short-range entanglement, and they have a unique ground state when you have periodic boundary conditions, when you don't have periodic boundary conditions, when you have an edge, it turns out that they show some interesting properties at the edge. Okay, they have an exotic edge, and that is what distinguishes different phases with short-range entanglement. Okay, so let's say you have some state with short-range entanglement. Maybe it's a trivial phase. Okay, so there's always some trivial phase. Okay, which means I can simply write it as a product of some particular state on a site, and then tensor product with the other sites. Okay, so there's a phase without any interesting edge states. And then let's say I have other states that are distinguished from this trivial phase. Let me call them topological. Okay, they have some edge content. Okay, so you can ask what are the different states that you have. If I give you a particular symmetry, there's some symmetry G, a group that tells you what the symmetry is. You can ask what sort of phases could I have. And one very general result you can derive, which I'll sort of give you an argument for, just to kind of show you how having a clear definition helps, is that the set of phases okay, so the simple way to say this is that you can add and subtract phases. Okay, so if I give you a state, which I tell you is a topological state, but with short-range entanglement, it's not just a member of a set. Okay, there's more structure than that. You can take a pair of these phases and you can add them together, and you will get another phase which is of the same kind, of the same class, but you can also subtract 2 phases. Okay, so the addition of phases is pretty simple. Okay, so I have one phase and I add another to it. You just think of the combined system. That together is a new phase. Okay, now you can also do, so when you have an abelian group, it means there's some sort of addition operation defined. But there's also a trivial element. There's an identity element. Okay, the identity element is just the trivial phase. Okay, that's the zero of your addition. Okay, and the way in which you do subtraction is that if I give you a particular element, okay, so let me tell you, I give you a particular phase. Okay, there's a way to identify the inverse of that phase. Okay, there's a way to get to minus of that phase. Yeah.
When you say the phases with short range entanglement, you're going to be looking at the topological phases, right?
Yeah, so it turns out to be complete, you have to also look at the trivial phase.
Okay. No, because the idea is that short range entanglement, you can have short range entanglement, many things that have nothing interesting, right?
Yeah, so then, okay, that would be just the set where trivial is the only state. Okay, so let me tell you, let's say you have a particular group of symmetries. Let's say it's Z2, for example. That was the symmetry we started out with. Okay, you're in some particular dimension. Okay, that's the data you need to give me. Tell me what the symmetry is and what dimension you're in. Okay, and once you tell me that, I should be able to tell you all possible phases with short-range entanglement, which respect that symmetry. Okay, and okay, so actually computing that may be hard or something like that. But even without doing any work, you can say that the output of this has to be a group, an abelian group, right? Okay, for example, if you look at topological insulators, the classification is always some abelian group, like Z2 or integers. Okay, so is that an accident or is that something more fundamental? With free fermions, actually, you can show that this idea of addition is simply adding bands together, filling more bands. Okay, but even in a situation where you have no notion of bands, that result still holds, that the set of phases should form this group where there's an addition defined. Okay, and the reason is simple, that you can do addition with this combination and you can do an inversion operation, which is, if you give me a particular phase, I want to find another phase which is such that when I combine it with this one, there are no edge states. Yeah, question?
Excuse me, is there a relation between the group G, which, if I understand correctly, is a symmetric group of the Hamiltonian, and the group of topological phases?
Okay, that's a very good question. So with certain restrictions, there's a way to go from this to that group. Okay, so for example, if you restrict your attention to, say, one-dimensional phases of bosons, then it turns out that this group over here is something called the cohomology group of G, with D equal to 1, okay, which turns out just to be the projective representations of G. Okay, I think Frank Polman will talk about that in more detail. Now, in higher dimensions, there's a conjecture that this continues to hold. But it turns out there's some problem with that in 3 dimensions, where we found an example where there's a phase which is not part of this cohomology conjecture with time reversal symmetry. Okay, so I would say that that's still an open question. There's a lot of work being done on it, but if you restrict these things sufficiently, there is an answer that is no. If you restrict G to be just internal symmetries that are unitary, then it's this cohomology group. But it's not very simple, and it's that I would say that for the purpose of this lecture, we'll be interested more in giving examples of these phases rather than trying to classify all of them. Yeah.
How does that work for the integral quantum Hall effect? I don't have to.
Yeah. Okay. So good question. So let me specialize to bosons for a moment. As soon as you have electrons, it gets a little more complicated. But even with just bosons, there are analogs of the integer quantum Hall effect where there are chiral edge states and you don't have any symmetry. So it turns out in 2 dimensions, even without any symmetry, there is a non-trivial group, which is a group of integers. And that actually turns out to be this additional set. Yeah, so, maybe what you're asking is there's an additional caveat that it has to be non-chiral state. Is that the question?
Okay. You said that the group has to be unitary, but if you take the Fermions in the D2 topological insulators, you have time symmetry represent unitary.
Yeah. So as soon as you go to another caveat was bosons, right? So as soon as you introduce fermions, even with internal symmetries, we don't know of this the general answer over here. People have computed it in various cases, but for example, for topological insulators, there's a complete classification of states. But it's not like a word I can use. It's not some name of G. Yeah. So, okay. So the last thing that I had to do was to tell you how to do subtraction over here. So you want to find a phase that when I combine it with any given state, I get no edge states. Okay, so any idea how we can do this? How to guarantee that there will be no edge states? Say? Time reversal, that often works, but there's actually an even simpler way of doing it, which is completely obvious. Yeah, so think of some way of not having any edges. So if I were to do something like this, okay, there's no edge, and of course there are no edge degrees of freedom then. But this is just the same phase that is turned around, right? So if I take a phase and I take one of the coordinates to minus of itself, okay, the Hamiltonian that you get will be the Hamiltonian of the inverse phase. You don't need inversion symmetry. Actually, it's a problem if you have inversion symmetry. So I give you a Hamiltonian for this region. Okay, you take this Hamiltonian and take the x coordinate to minus of x. You'll get a new Hamiltonian, typically if you don't have inversion symmetry. Right? And that is the Hamiltonian for this one. Okay, so let's say this is h of x. This is h of minus x. So if you did have inversion symmetry, these two Hamiltonians would be equal. So then you would require that this phase is the inverse of itself. Right? Because when you put them together, you can of course continue this around like this, and this of course has no edge states. Yeah, that's right. This is a bit of an overkill for that case because there's a free fermion way of thinking about it. But if you give me a phase and I just do minus of one of the coordinates, this could be in any dimension actually. Okay, so you have an inverse phase, and that completes this thing, mapping to an abelian group. Okay, so this fact is actually very powerful, and anyone who's worked in this area will, you keep using this fact in order to eliminate certain possibilities. Okay, for example, if someone told you that Z2 topological insulators, so we know that there's a trivial and non-trivial element there. Someone told you that there's one more topological phase. Okay, so the Z2 is extended to, with interaction somehow you have the trivial phase, you have Pi, and you have one new phase. That's it. Okay, so you know immediately that can't be right. Okay, because we know that if I take two copies of the Ti, it's the identity. Right, and then I have this phase x, but I should be able to combine this with x and get another phase. Okay, so it has to be that there's another one which is. Okay, so there are things like this that you can use, ideas like this that you can use by knowing that it's an abelian group. Okay, so that maybe it's a little abstract till now, so let's actually get down and talk about some examples. So the plan is that I'll tell you a few examples of these topological phases with short-range entanglement. Okay, and these will be of bosons or spins. Okay, and the idea is that we're going to work towards this result, that we have this new set of phases for the electronic integer quantum Hall effect. Okay, but we'll start with 1D. Okay, so you'll see that I think Frank will also talk about this, but I'll do it in a different way so that it's something that we'll readily be able to generalize to 2 dimensions. We'll construct a topological phase which is short-range entangled in 2 dimensions with just bosons or spins. Okay, and until about 3 years back, we didn't believe that there were such phases. Or nobody had asked this question very sharply to know that there was such a phase. Okay, the one-dimensional phases actually were well known before. In a way, we have just understood them better. But in 2D, it was something new. Okay, so let me start with the 1D example. Okay, and the special thing about 1D is not only we have an example of short-range entangled topological phase of these bosons or spins, that phase has already been seen in experiments. Okay, and doing the analogous thing for 2D and 3D is going to be left as an exercise for all of you to find analogs of realizations of these things, which maybe the experimentalist can look for.
Can these interacting phases be irreversibly connected to non-interacting descriptions of phases?
So I'll be talking about these the cases with bosons or spins, where the non-interacting description is actually very boring, right? So if I think of a spin system without any interactions, I guess the only way to think about that is maybe as independent spins. So they can't really do anything very interesting. Bosons, if you have bosons without any interactions, we just write down some quadratic Hamiltonian. Let's say the charge of the bosons is conserved, then you would simply get some Bose-Einstein condensate at 0 temperature. So by specializing to this case, we are sort of guaranteeing that you have only interacting phases that you're talking about. Okay, so there's no direct way in which they are connected to a non-interacting model of bosons or spins. Okay, now sometimes you can rewrite these in other variables where there's maybe a fermionic description in terms of emergent fermions where the fermions form some topological phase and then get confined or something like that. But there's no local description. If you have just local operators and you're talking about what they're doing, there's no description of these topological phases in terms of free particles. Okay, so that actually is maybe important to emphasize a little more. I'll do that as maybe when we look at this example in some detail. So the somewhat surprising thing is that if you take this very simple Hamiltonian, which is just spin 1 moments on a chain, okay, with Heisenberg antiferromagnetic interactions. Okay, so this is spin equal to 1. So there are 3 states on every side. There's a 0 and then there's a plus minus 1 spin projection on every side. Okay, just combine them with the most natural spin coupling you can think of, Heisenberg coupling. So it's known by numerical simulations and things like that this is actually a gap phase and symmetric. Okay, and it has non-trivial edge states. Okay, the edge states are essentially spin 1/2, which is rather unusual because you built up everything out of spin 1 particles. Okay, so if you were some sort of microorganism that's living on this line, and your universe only has integer spins sitting around, but when you get to the edge, you discover that amazingly there's a spin 1/2. There's something that you can only interpret as spin 1/2. Okay, so although you just have rotations of space, SO3, okay, where doing a 2 pi rotation is just the identity element, you find a set of states at the edge where doing 2 pi actually does something. It changes the sign of these spins. Okay, so this has sort of been experimentally observed. Okay, on some nickel-based magnets. So nickel is usually spin 1. Nickel. I'll try to give the exact reference in the lecture notes. And one way they see it is they put in impurities, they put in zinc impurities, which takes a single long chain and breaks it up into little segments of spin 1 chains. Okay, and then you see that there's a contribution to the specific heat, to the magnetic susceptibility from these spinor halves that appear at the edges. Okay, and the contribution grows the more impurities you have because you have more of these chains. Okay, so this is one example that is very naturally realized. But in order to get some insight, some direct handle on these kind of phases, it actually helps to go to a lower symmetry. Okay, so this has the full spin rotation symmetry, SO3. Okay, so this is any rotation about the 3 spin axes. It turns out it's sufficient to preserve the essential physics if I just retain the 180-degree rotations. Okay. So, for example, if I take a spin and do a 180-degree rotation around the x-axis, okay. Okay, so this is actually the Z2 symmetry that we had before in this particular model. Okay, it takes sigma z to minus sigma z, sigma y to minus sigma y, but leaves sigma x unchanged. Okay, so this was the Z2 of the Ising model. Okay, and now I have 180-degree rotation about, say, the z-axis as well, which changes the sign of the x and y components. Okay, that's another Z2 symmetry. And there's a third about the y direction, I guess. But that turns out to be just a combination of these two. Okay, so the symmetric group, which is 180-degree rotations about the cardinal axes, is simply Z2 times Z2. Okay, there are 4 elements. One is the identity, and the other 3 are the rotations about the different axes. Okay, so it turns out with just this much symmetry, we can actually stabilize this topological phase. And the advantage of having a smaller symmetry is we can write down a model that's exactly solvable, where you can see all of these things in detail. Okay, a bit like how we did it for the toric code model. Okay, and we'll be able to verify that this is short-range entangled, but nevertheless has some edge states. Okay, so another thing this will help us do is we'll actually get a physical picture of these topological phases. This actually doesn't work for every one of them, but it works for a set of them, and when it does work, it's actually very intuitive. So the way we'll think about these topological phases is of having defects that actually bind some quantum number. Okay, so we'll think of it as decorating defects and condensing them in order to get these topological phases. Okay, so let me actually go back to this particular model for a second. This is one of the Z2 symmetries. And we want to now think of something which has 2 of these Z2s. Okay, so you could actually start with spin 1 and keep these to be rotations, or I can just come up with a model that's more convenient. Let's say I have 2 kinds of sites. Okay, so what I'm going to do now is and the symmetry is going to be Z2 times Z2. Okay, a pair of these spin rotation symmetries. Okay, so I have sigma spins on this set of sites below, and let's call it tau spins on this set of sites. Okay, and there's a Z2 symmetry. One of the Z2s is sigma z goes to minus sigma z, and the other Z2 is this tau z goes to minus tau z. Okay, so when we are in this topological phase, we have to make sure that these symmetries are preserved. Okay, so we're going to assume that there is no spontaneous breaking of symmetry. And one way to think about the symmetric state, if you go back to this Ising model, we have this ordered state and the disordered state. So if you think about how you get into this disordered state starting somewhere here, you have all of these spins aligned, and then you begin to have quantum fluctuations that end up killing this order. And the way in which quantum fluctuations do that is by creating defects. So you have domain walls where the spin is up, and then at some point the spin becomes down, and continues being down for a while. Okay, so that domain wall, if it moves around, it can end up scrambling the spin and end up restoring the symmetry and getting you into this phase. Okay, so this process of restoring symmetry, you can view as taking these topological defects, the domain walls, excitations that look like that. Okay, at this point where the spins up go to spin down. And you can think of this as a particle. This particle begins to move around, and that's what gives you the quantum disorder. Okay, so the distinction that we'll see over here, what will actually give us the new phase with edge states, is that the thing that will move around is not just a domain wall, it's actually a domain wall that's bound to one of the other spins. Okay, so if you like, it's a decorated domain wall. It has something more than just a plain vanilla domain wall associated with it. And when that proliferates, moves around the system, it ends up giving you the topological phase. Okay, so you can actually see that explicitly, and that'll be the, let me just describe that in some detail. Okay, so we'd like to think of disordering okay, so just for our, as a sort of thought experiment, let me say I start in the state where the sigmas are ordered. Okay, the sigma is ordered, but the taus are disordered. Okay, so a picture of this is I have spins up on the sigma sides. I've broken one of the Z2 symmetries, but I've kept the other Z2. Okay, the tau sides are preserving the spin up to spin down symmetry. They're along some x direction, let's say. Okay, so I want to start from this state and imagine doing some quantum disordering process that will land me in the topological phase. Okay, now if you simply had domain walls of the spin and you were to proliferate them, you get the usual disordered phase, the trivial phase, okay, which has all the symmetries. But if you do the following, let me say I pick a domain wall. Okay, that's a domain wall of these sigmas. But at the same time, when I pick this domain wall, there's a point over here where the spins change. So conveniently, there's a tau spin sitting at the exact same location. Let me say I flip the spin on this one. Okay, so I flip it from the plus x direction to the minus x direction. Okay, so I have a combination of a domain wall and a spin flip. Okay, and I claim that when I proliferate this kind of object, I restore the symmetry. I make this, I get rid of this ferromagnetic order in the sigma chain. I get something which has all the symmetries, but this will have edge states. Okay, so there are many ways of showing this. You can try to think of some intuitive ways of doing this. But because this is one dimension, you can really do something very complete. We can actually write down a Hamiltonian which will encourage this kind of binding. Okay, and then we'll analyze this Hamiltonian and show the phase that you have is actually one which has edge states. Okay, so let's say I wanted to encourage this kind of binding. What I would do is I would take a pair of these sigma spins and check if it has a domain wall or not. Okay, and when it does have a domain wall, I'd like to flip this tau spin that's above it. Okay, so the way you would do that is you have some sigma z on a pair of adjacent sides in this lower chain. Okay, so let me label these sides by I. Okay, and this is somewhere in the midpoint, so I'll call this I plus a half. Okay, that's some I bar. Okay, that's where the tau spins live. Okay, so this is site I. There's a tau at site I plus a half. Okay, so this checks whether or not you have a domain wall. If you have no domain wall, if these sigmas are aligned, then I just have the usual spin flip, tau x. Okay, the usual transverse field, like this over here. But if I have a domain wall, then these sigmas will have opposite, this product will be of the opposite sign. You will get a spin, you want a spin flip along the opposite direction. Okay, and that will change the sign of this coefficient for the tau x. Okay, so this is a model that will encourage this kind of binding. Okay, you can also make it symmetric between tau and sigma, because ultimately you want okay, so you have these two sets of terms. Okay, so it's easy to analyze that this is short-range entangled. So let's do that first. So let's assume we have this with periodic boundary conditions. Okay, so we have a chain with periodic boundary conditions. Okay, you can easily check that it has a unique ground state. And it has a gap. Okay, and one way to do that is to notice that actually all of these terms, they commute with one another. Okay, so these operators commute with one another. You can take a set, you can take sigma z, and take the adjacent one. Sorry. Okay, so this is a pair of terms. These three spins and these three spins. Okay, and this is the one that you might worry doesn't commute because it has some overlap. So in fact, if you look at it, it looks problematic because there's a tau z and a tau x. So the Polya operators don't commute, they actually anti-commute. Okay, but that's compensated by the sigma z and sigma x that exactly undoes that. Okay, so you have a pair of operators that individually anti-commute, so together they commute. Okay, so all operators commute over here. So you have a set of n commuting operators. So n is the number of sites in the system. For every site, you can think of this as being an operator that's centered on a site. The central site over here. So every site you have one operator, and they all commute with one another. Okay, so with periodic boundary conditions, it implies that there's a unique ground state. Okay, so in a way, you can think of this as some modified transverse field operators that looks like that. Okay, so they commute with one another. They're like Pauli operators. They're just some modified transverse field operators. Okay, and for every site you have a transverse field operator that sets it on some unique state. Okay, so there's a unique ground state. So if you want to make an excitation, you've got to flip one of these modified operators, and that causes some energy. There's an energy gap. Okay, so this is short-range entangled. It satisfies these criteria. It's fully symmetric. It doesn't break the symmetry. So all we need to do now is to show it's not trivial. It actually has something interesting at the edge. Okay, so this was to show that it is short-range entangled. Okay, so now we want to show it's topological. So let's say you have edges now, not periodic boundary conditions, something with edges. Okay, so when you have an edge, let's just analyze one of the edges. There's something else happening at the other edge. But let's say that's very far away. Don't worry about that. So if you look at this edge over here, everything we said before holds. You have these commuting operators that you can put them, each of them in their ground state. Except for one caveat, which is there's one operator that you can't quite write. Okay, so because you chop this chain at this particular point, there's one operator that involves 3 spins. This one here, this, and this one here. Okay, but I terminated the chain over here, so I'm missing this operator, this last operator. Okay, so so you have the Hamiltonian with these edges where there's a last operator, which is sigma x. Let's call it 1. Yeah, so if you had this term in the Hamiltonian, this would be a problem, right? Because you broke one of the symmetries. So we're going to set this term to be 0. Okay, so that's the only consistent thing that you can do if you want to terminate this chain over here. So you end up with the first term actually being this one over here. I guess maybe I should write that as... Okay, so the first non-vanishing term, which preserves all the symmetry, is this one that begins over here and involves these 3 spins. Okay, so because of this, you're missing one operator, the first operator over here. Okay, and that's going to give us a 2-fold degeneracy. Okay, you'll see that in a minute. Okay, so the Hamiltonian begins over here. So I can find something that commutes with the Hamiltonian to show that there is an edge degeneracy. So I can write, for example, sigma x. Actually, let me call this sigma z just for consistency. Okay, so this is an operator that commutes with the Hamiltonian. There's just sigma z at the end point over here. But that in itself doesn't guarantee a degeneracy. Okay, so you have something that commutes with the Hamiltonian. It means that you can diagonalize them simultaneously, but doesn't necessarily mean there's a degeneracy. You could have a unique ground state. Okay, it could be that there's no edge degeneracy when you just find a single operator. But it turns out you can find another operator that commutes with the Hamiltonian. Okay, and this is, let's say I were to take sigma x, 1. Okay, this in itself doesn't commute because it has a problem with the sigma z, but I can multiply it by an appropriate tau operator on the next site, and together this pair commutes with this part of the Hamiltonian. Yeah.
But this is overkill, right? In a sense, you don't need the whole spectrum will be 4-fold degenerate with 2 edges in this case.
Yeah.
But you only need the ground state proof as the degeneracy proof that you have state, right? So this is kind of like an overkill applying these operators, right?
No, this is what tells you that you have 4-fold degeneracy.
No, the whole Hamiltonian, the whole spectrum will have the 4-fold degeneracy in this case, right?
Yeah, but
So, for example, like in the Kitaev chain, you have a 2-fold. If I just in the free fermion, the full spectrum has 2-fold degeneracy. Like if I add interactions, that 2-fold degeneracy is maintained only in the ground state.
right.
So in this case, it's the same thing, right?
That's right, yeah. But to prove that it is degenerate, if I just look at this Hamiltonian, how do you know it's degenerate?
Yeah, no, you find operators, but what I'm saying is that
Right.
just to commute with a full Hamiltonian is not necessary.
That's right, yeah. It's just to show for this particular model that you have this degeneracy. So both of these operators commute with the Hamiltonian. Okay, but they don't commute with each other. Okay, so they are like Pauli operators. Okay, so when you have this condition, you can easily show that the ground state has to be, in this case, twofold degenerate, because if you were to let me do it, sigma c. Okay, so you had some particular quantum number with the sigma z operator. You could act sigma x on the state. Okay, and you're guaranteed that now when you apply sigma z, you get the opposite eigenvalue. Okay, so if for some reason this had a unique ground state, you could, which was labeled by some particular eigenvalue of sigma z, you can act with the other operator that you have. You get another state, and you can demonstrate that this state is different because it has a different eigenvalue under sigma z. Okay, it's the usual reason why spin a half always has degeneracy. Yeah.
Okay, so this shows that everything is degenerate. Right?
That's right. Yeah.
How would you go about it if you expected only the ground state to be degenerate? Is there some general procedure that you can have, or does it need to be inspired by knowing the model?
Yeah, so that's a good question. So if it was just the ground state that had this degeneracy, for example, in the spin, the first example that I gave, the Heisenberg model with spin 1. So that's a case where you don't have this sort of algebra. So there is something like an exact ground state for that model. If you change the Hamiltonian by adding biquadratic terms, you can get it to a special point where you can write down a ground state wave function. But it's not an exact solution in this sense. Yes, this is an exact solution in the sense that not just the ground state, all the excitations can also be computed in a simple way. Okay, so that's, whereas for this AKLT point of the Heisenberg chain, you have just candidate wave functions for the ground state, which can be shown to be, exact wave functions. Okay, and you also have a degeneracy in that particular case. But,
Sorry, do you have a SUSY? Because I have the supersymmetry.
For which one?
Do you have a supersymmetry, the hidden supersymmetry model?
In this model? Yeah, so this model can be mapped to free fermions. Yeah, so if you think about what this three-spin interaction is, it's simply, you can fermionize this model by the usual Jordan-Wigner kind of fermionization. And this is a fermion hopping by two sides. So if you have just second-neighbor hopping of fermions, that will give you a Z2 times Z2 symmetry. The fermion parity is conserved on each of the sides, each of the sublattices. And this is, this term in between is just part of the Jordan-Wigner string. Okay, so that's why this particular model is special, and you can say all these exact statements about it. But in general, if it's just the ground state that's exhibiting degeneracy, you pretty much have to solve the model. Unless you're lucky and you have this kind of AKLT state. You have to solve it maybe numerically or something like that. Yeah.
Just a simple comment. You can generalize this to any dimension, right? Because you can take a cluster, you can think about these guys as a spin with spikes. And you can make them commute in any dimension. Right?
That's right, yeah. So we'll try to extend it to 2 dimensions now. And we'll try to keep this physical picture. Like you're saying, you can try to generalize the algebra, but what I'll try to do is to generalize the physical picture. That I have some defect that is being condensed, and the defect is not the simple defect. It has some other quantum number associated with it. And that will allow us to get the 2-dimensional example. Okay, so Okay, so the one way to lift this degeneracy at the edge is simply to break the symmetry. Okay, and then you can add a term like this, for example, that will polarize the edge. So this degeneracy at the edge is protected by symmetry. That's that's what makes this particular phase distinct from the trivial phase. Okay, it's only distinct when you have the Z2 times Z2 symmetry. Okay, any more questions for you here?
Why does ground state degeneracy apply edge states?
So in this particular model, if you have periodic boundary conditions, there's no ground state degeneracy. Now you cut the model, and it's gapped in the bulk, right? So now you cut the model and you find degeneracy. So it's got to be something associated with where you cut it. Because in a gap state, you can just think of, you have this Hamiltonian and you begin to weaken one particular bond over here. That influence is not going to spread deep into the bulk. Now, of course, in this particular model, you know the wave function of this, everything is known, right? So you can tell that the two ground states that you have only differ by application of this operator sigma x, for example. And that's a local operator that's sitting at the edge. So it's an edge degeneracy. Yeah, I think Frank will talk about, in 1D, there are more rigorous results because of this matrix product representation that tells you the only way in which you can get degeneracy for a gapped phase is through these edge states, and everything is very sort of well controlled in 1D. Okay, but 2D is a little more complicated, and what we'll try... Yeah.
Could you use another sigma acting on another side to make these non-commuting symmetries? Like you can choose like sigma 10 and it wouldn't work?
No, it won't commute with this Hamiltonian then. It's only the edge spin that, because you don't have this term, the edge spin is special. Okay, so now we want to go to 2 dimensions, and the most obvious generalization of the domain wall defect is a vortex. Okay, so if I have a superfluid in 2 dimensions, you have a point-like defect, which is the vortex, and again, the insulating phase, where you restore the symmetry, you can think of the insulating phase as arising from condensing vortices. Okay, so there are a lot of vortices running around in the ground state. That kills the superfluid, restores the U1 symmetry, and that's the insulator. Okay, so to find a 2-dimensional example, okay, the symmetry that we'll consider is, it's natural to consider a U1 symmetry so that we have vortices. And because I want to make these vortices non-trivial, somehow different from regular vortices, let me actually assume that I have 2 of these U1s. Okay, and I'm going to take the charge of one U1 and attach it to the vortex of the other one. Okay, so what does it mean to have 2 U1s? So you can think of the following situation. Let's say you have some plane in which you have 2 kinds of bosonic atoms. Okay, so there are atoms A and B. Okay, and so the number of these atoms is individually conserved. So one way to say that is that you have 2 U1 symmetries, which is the phase of each of these species of atoms, and you can rotate those phases, and that's what gives you the individual number conservations. Okay, and we want to think of a topological phase where I take vortices, let's say, of the A particle, bind that to a charge, a B charge, proliferate those defects, and end up getting a symmetric state, which is exotic and has got these edge states. Okay, so okay, that's the idea. Okay, so we'll do this in 2 different ways. Probably I won't have time for both today, but one is we'll actually write down a concrete model. Okay, a little bit like what we did for the 1-dimensional case, but because this is 2D, we won't quite be able to do it in as much gory detail as we did over here. We'll think of coupling 1-dimensional tubes, okay, each of which carry these bosons in a particular way so as to end up in this topological phase. Okay, and that will tell you why you have edge states that are gapless, protected by these symmetrics. And the other way we'll do it is to write down a topological field theory. Okay, but maybe that will be more believable once you have this concrete, realization of this phase.
So this is the Wiltshire final theory.
Sorry? Yeah, right. Okay, so before I do that, I'll have to tell you how to describe a one-dimensional tube of these bosons. So let me sort of give you a crash course on 1D bosons, Luttinger liquids, if you like. Okay, and we'll use a bosonization approach. So it may seem a little paradoxical that we're trying to use bosonization to describe bosons. But in fact, you'll see that it's somewhat more convenient. It's a more convenient way of writing down a boson Hamiltonian. Okay, so once we know how to do 1D, we'll be able to take them and couple them together. Okay, so let's say I just have some chain of sites on which I have bosons hopping. Okay, some boson B that hops between these sites. And you can try to write down a Bose-Hubbard model, if you like, some repulsion term that costs you energy depending on the number of bosons you have on a site, n squared, and then there's some hopping term. Okay, so I've kind of skipped a step over here. So you'd really like to begin with boson operators like BI, the canonical operators for bosons, but you can rewrite these as in a number phase representation. Okay, there's a number operator which is just B dagger B. So a single boson on a particular site, you can write it in terms of the number and the phase. And if you have a large number of bosons on every site, you can think of this operator as being roughly a number. Okay, so it's essentially, B is essentially just this phase, at least for the long distance physics that we'll be interested in. I'll just write it as like a rotor, just the exponential of a phase. So when I hop a boson, when I do B dagger I BI plus 1, that is just e to the I phi I minus phi I plus 1. That's U times n squared. Some sort of charging term, if you like.
And use just a number?
Use a number, yeah. Okay, so this term just represents hopping of bosons from one side to another. This is some energy penalty that you pay. Okay, and as all of you know, if the filling is right, there are actually two phases in this model. There's one phase where the repulsion is very large, where you have an integer number of particles per site. That's the insulator. Okay, so as I increase this ratio J over U, if I'm at some integer filling, I have insulator, Mott insulator, and I have a superfluid. Okay, so superfluid in some algebraic sense, but it has the property that things will flow without any resistance. Okay, that's the limit where this hopping is very large, and you can ignore this charging term. Okay, so we'd like some way to see this from a long distance theory, not something that is as detailed as this, this is really a lattice model. So one thing you could imagine doing is, let me convert these differences into derivatives, expand this and expand the cosine, and that's sort of a harmonic Hamiltonian. It's like un squared plus j gradient of phi squared. Okay, this gradient is just derivative with respect to x. Let me write it as x. Okay, now the problem with this model is that it can only give you the superfluid. Okay, there's only one phase in this model, regardless of what the ratio of these parameters are. You're always in the superfluid phase. Superfluid just gets weaker and weaker the larger the U is. Okay, and the reason you only have one phase is that you throw away too much when you expanded this cosine. You throw away the fact that you can have vortices. Okay, so when you have a cosine, you can have phase rotation by 2 pi. It forgives that kind of phase rotations. Whereas this gradient doesn't forgive a 2 pi rotation. Right? It will penalize a 2 pi rotation. Okay, so in order to get this to be the complete Hamiltonian, you need to put back the vortices. You need the Hamiltonian to also include the possibility that you have vortices in your theory. Okay, so the way to do that is one way to do it is, that's why it's useful to write down this bosonized description. Okay, so you can ask, what is a vortex? Okay, so this is a vortex in space-time. Okay, so you have space x and time. At some particular point, you want that the phases of this boson changes by 2 pi. Okay, that's a vortex, whereas on this side there's no phase change. Okay, if you expand this out, this is a vortex that's winding around. Okay, and the operator that will do that for you, rotate the phase of the bosons by 2 pi, well, you just have to multiply by the conjugate operator, which is n, and the phase that you want, which is 2 pi. Okay, from this position x to infinity. Okay, so this operator will insert a vortex. Okay, this is a vortex insertion operator. Okay, so the n hat is, of course, conjugate to phi. Okay, maybe I should have written that. There's a commutation relation over here. Okay, they're canonically conjugate as usual. Okay, so you can think of n as translating phi. If I put it up in the exponential and I translate it by exactly 2 pi. Okay, so it's useful to define a field that does this. So if I define a field such that the derivative of the field is 2 pi times n. Okay, this vortex insertion operator, if I integrate both sides, this vortex insertion operator is just the exponential of this field theta. Okay, so you have this nice symmetry between bosons and vortices. E to the I phi is the boson, e to the I theta is the vortex. Okay, putting in a vortex. Okay, so then you can write a more complete Hamiltonian, which actually has the physics of vortices in it. Okay, so the number density I'll replace by the gradient of theta. There are some 2 pi's, but I won't really worry about the 2 pi's. Okay, then there's some gradient of phi. So these gradients are, of course, just in the x direction. Okay, now I insert the possibility of having a vortex insertion. Okay, and the commutation relation is that it's just this number phase commutation. So dx of theta and phi. Okay, so this is at point x prime. Okay, this is just the number, essentially just the number density times the phase. You just rewrite it in terms of these theta and phi. Okay, so this gives you a complete specification of this problem, but it has the vortices in. Okay, that's the advantage of writing it in this bosonized form. And you can see the 2 phases from this description easily. Okay, so there's one phase where you ignore this term. That's the superfluid phase. Okay, and there's another phase where this term is the most dominant part of the Hamiltonian, where this lambda is large. In that case, you want to pin this angle theta. Okay, so you pin this angle theta equal to 0 everywhere, and that corresponds to the Mott insulator. Okay, so having theta constant means that, and if you have any change in theta, that's going to be gapped. Okay, because you'll have to move from one minimum of the cosine to another. That's going to cost you energy because you're going to violate the minimum of this cosine. Okay, so that changing of theta corresponds to charge density being put into the system. So that's the insulating phase, okay, where it doesn't like to have charge density, anything apart from the uniform charge density. Okay, so it's very easy to read off the 2 phases over here. Okay, and once you pin this theta to be something unique, you have no ground state degeneracy. You just picked a unique insulating state. Okay, so this will be the description of the 1D system that we're going to use. And now we'd like to couple the different 1D systems together. Okay, any questions about this? Yeah.
How do you determine lambda?
Yeah, so lambda, for our purposes, we won't really be worried about the exact value of lambda. That will, of course, depend on what this J over U ratio is. But we want a description which will, in principle, allow us to capture the two phases. And sometimes there are more phases. I mean, there could be more phases. Like, for example, you could think of some cases where you have a topological Mott insulator. If you have a little more symmetry, you can do that. And that corresponds, for example, to a different sign of lambda. The lambda is positive or negative. That can actually affect what phases you get. But we'll stick with the simple scenario, and we'll sort of, try to use this for the 2D example. Yeah?
Can you explain again why the boson operator is pure phase?
Yeah, so if you're just interested in long-distance physics, you can replace it by the operator as just pure phase. It has the same symmetries as the operator as just pure phase. Now, if you want a microscopic derivation of that, you can think of the following scenario. Let's say there's a very large number density of bosons. So instead of having a Mott insulator with 1 particle per site, let's say you think of something which has, say, 100 particles per site. Okay, so then this operator, you can write it as some constant plus some fluctuation part, which is the operator part of it. Now, this fluctuation will be of order 1 typically. So you can make an expansion where this is essentially just square root of n bar, the first term. So it will simply be square root of n bar times e to the minus I phi. And okay, this is just a C number, right? So this will appear over here when it will renormalize the J. J will get pushed up by this number n, but it's essentially just this cosine. Phi is compact, yeah. Yeah, so that's right. In the lattice model, phi is compact. You lose that feature when you get to the continuum model. And that's the problem with this naive continuum model.
We go back to compact.
Yeah, so this is a way to keep the essential physics of compactness. So one way to think about it is, let's look at this particular, the way this is defined. This is like a tight binding model, right? The number, you can label it by the number operators on each of the sites, and you're just hopping these bosons. Now, there's another limit in which you can think about a tight binding model, which is sort of the weak binding limit. If I just had a band structure, you can either think of tight binding or you can think of weak binding. And in a way, writing it like this is the weak binding regime of this lattice. So yeah, I can make that a little more clear. So let's try to do an exact rewrite of this. I guess I'm out of time. Is that right? Maybe I'll just explain this and... Okay, so what you can do is you can do an exact rewrite of the problem by saying that I have a field theta, which is going to be just 2 pi times n of x. Okay, and compactness of phi is the same as saying these numbers are integers. So if I look at this field over here, theta, as a function of x, let's say there are some particles at certain positions. Every time you encounter a particle, you move up by 2 pi. Okay, that's what this relation means. Okay, so this theta field is always 2 pi times an integer. Okay, that's strictly speaking what we should do if you want to be exactly faithful to this model. Okay, now what you can do is you can try to soften that constraint a little bit. Instead of being very, strict about this constraint, you can say, let me think of theta as being a field that takes on any value, but it likes to take values that are 2 pi times integer. Okay, that's a bit like the weak binding limit. You don't say that things are forced to be on sites. You say they like to be at the bottom of some potential. So let's put on a potential that would like to keep theta at 2 pi times an integer. Okay, but that's exactly this potential over here. That likes to keep theta at 2 pi times an integer. So you have some of this physics built in. Now, of course, if you want microscopically to know what's the right value of theta, that's going to be very hard. You also have higher order terms like cosine 2 theta and so on. But from some moral sort of perspective, this model captures the two phases. From long distance perspective, it's okay. Yeah.
So what happened with the BNP dagger operators? What was the point? I mean, it looks like you had a model written as n and phi, and you wrote a commutator, and then you just wrote another commutator with some variables.
Yeah, so some people like to write everything in terms of these canonical bosons. And what I'm trying to say is that writing in terms of number and phase is equivalent to writing in terms of canonical bosons, up to some details. But it's much easier to analyze the model with number and phase. So the usual if you have this sort of relation between B and number and phase, you can verify that B dagger B has the usual commutation relation, assuming that number and phase are just conjugate.
So is that the bosonization going from B and B dagger to n and phi?
No. So that is just sort of a way to define a model that's easier to analyze. The bosonization is to go to this theta variable. Yeah, so to write everything in terms of a pair of these bosonic fields, where this theta, where you have these, vortex insertion operators.
But I mean, you didn't do very much. You just replaced n by partial theta, and you call that your new variable. Is that fair?
Up to this cosine, right? If I didn't have this cosine, that's what I'm doing. But the cosine is very important because it allows you to get the insulator. And we'll see that when we have coupled chains, we're going to just modify this cosine term. Okay, this is what inserts the vortices. We're going to modify the vortex. Okay, I think I should stop there.